Welcome to Little Wild Experiences. Today we're going to talk about exoplanets and the influence of AI on their discovery. It's a very special episode today because we have Dr. Gartrelle who will be talking about exoplanets and how they're discovered and all these kind of cool things. So, Dr. Gartrelle, he's a planetary scientist who focuses on solar systems and small bodies. He holds a PhD from the University of North Dakota in aerospace science, where he specialized in asteroid spectroscopy. And he has master degrees from UND and from George Washington. He as well as a BA from University of Colorado. He has written a number of peer-reviewed articles in asteroids, asteroid mining, astrobiology, and other topics. He has completed a simulated mission to Mars and worked on multiple space-related projects for NASA and overseas. He is currently serving as a member of a science team planning for a future robotic lunar mission, and he has an asteroid named after him. So let's give him a good hello to Dr. Gartrelle. Hi. Thank you. Thank you.
Good
I did it.
afternoon. It's great to be here. Thank
Yeah.
you for having me.
Thank you, Gordon. I know last time we had a hiccup, so today is going to go well.
Of course.
All right, so let's talk about exoplanets. I want you to tell me about that. What do we
Okay.
know about?
What do we know? Well, let's step back a bit
Mm-hmm.
and let's try to define exoplanets and planets. So we'll start with planets, okay? And we
Oh,
because we understand planets, right? We live on a planet and we live on one of 8 planets in our solar system. So the definition, official definition of a planet, which was crafted in 2006 by the International Astronomical Union over in Paris, said that a planet must orbit the sun. So it must be a body that orbits the sun, okay, our sun. It must be big enough to have gravity to force it into a roughly spherical shape. And it must be big enough so that its gravity has cleared away any objects of similar size in its orbit around the sun. And this definition applied specifically to our solar system. They specifically said the sun and around our sun. They did not really mean for this definition to apply to things outside the sun. And one of the reasons was in 2006, although we knew there were planets, we had confirmed uh, planets around other stars, we didn't know a whole lot then. We also didn't know as much about our solar system then as we do now. So that's a whole nother discussion, which we'll get into a little bit later. But if you take that definition and you uh, loosely wrap it around the concept of other stars, an exoplanet becomes loosely defined a body in orbit around a star other than the sun with some caveats. It has a mass estimate that is equal to or less than that necessary to achieve fusion, meaning it's not a star or it's not a brown dwarf, right? It's not uh, creating helium out of hydrogen from its core. Okay, so it's stable. It must be relatively spherical. Kind of interesting definition with respect to exoplanets. We'll also talk about later. It's not a star or a stellar remnant. Many stars in the galaxy and in the universe are binary stars. So they're 2 stars and 1 star orbits the other. So an exoplanet is not one of those. An exoplanet has to be validated and reviewed by others. So you and I can't go in the backyard with our telescope and discover an exoplanet and announce to the world, hey, I've discovered an exoplanet, without other people, credentialed people, coming in and taking their own observations and validating that scientifically to make sure that we can confirm it from a variety of perspectives. So, so um, exoplanets orbit other stars. We, in our history, have romanticized about planets around other stars. We see it in science fiction literature, the old Buck Rogers, Forbidden Planet stuff, Star Trek, Star Wars. We have people wearing costumes to Star Wars conventions and going to movies and watching it on TV and reading books. And so we we like the idea. We obviously popularly like the idea of planets around other stars, but we didn't know that that was a possibility until about 40 years ago. People began to suspect that there were planets scientifically. We're able to perhaps see some things that they thought were planets, but there were no confirmations made until 1992. Wolskan and Frail discovered um, a planet around a stellar remnant, so a dead star, pulsar, stellar remnant that kind of blinks with regularity, and that was in 1992. In 1995, um, the first planet was found around a sun-like star or a main sequence star, and that was PEG 51b. Um, and since then, the discoveries have, in the last 40 years, the discoveries have come pretty regularly. Um, we now have confirmed about 5,500 exoplanets, and we've discovered them through a variety of means, some through ground-based observations, particularly early on, and then as things advanced, through space missions, through existing space missions like the Hubble and Spitzer space telescopes, and then specialized exoplanet missions like Kepler and TESS and Europe's CHEOPS, which those focus specifically on looking for exoplanets. And so we found about 5,500 of these things. We found them in the nearest star to us, Proxima Centauri. Proxima Centauri uh, is 4.2 light years from Earth, and there is a planet there, Proxima b. We found them fairly far away. We seem to be finding them just about everywhere we look, but there are some caveats to that, and we'll talk about that as we go forth.
What's the importance of discovering these exoplanets? Why scientists take these discoveries seriously and then keep working so hard on trying to discover what are they and where they, all what make this planet be there? Like why it's so important to get to know more about it?
Well, obviously, we have an innate curiosity as human beings to know more. That's in our DNA. That's been in our DNA since we've been in existence. So we always want to know more about the environment in which we live. Um, we want to know more about life, um, how life formed, uh, where life is headed, and is there only one form of life in one place, Earth? So exoplanets kind of gives us all of that, um, plus the Star Wars aspect of actually going maybe touching some of these worlds in the very, very distant future, and maybe engaging with other life forms or intelligences out there. So there's a lot of reasons that we want to study that. It also helps us understand how we came to be, um, because there's a vast amount of knowledge to be gained by looking at how other solar systems form, how they're composed, what they're composed of, how they've evolved over time, how they've evolved uh, towards the end of their lifespan. Our solar system's in about the middle of its life. The sun is kind of a middle-aged star, right? It's in its midlife crisis. It probably has a Porsche and a nice haircut and gold chain. It's about there, and still got about half of its life left to go. So what's going to happen as our star evolves? What's going to happen to our star? What's going to happen to our planet? What's going to happen to our solar system? There are examples of that out there in space that we can detect, we can observe, we can learn from, we can analyze, and we can make conclusions about.
So in simple English, because this is a very complex topic and I'm sure for many people. So how these planets are discovered?
Okay.
Um, yeah.
Wow. Okay. So there are five main ways to find an exoplanet. Um, the first, and I'll go through each of those just really briefly. The first one is transit. And transit involves looking at a star from either the surface of the Earth or from a space platform, space telescope, um, Hubble, Webb, uh, Kepler tests as transits. You're looking at a star or group of stars, and you're looking for a little dot that passes in front of that star. So if you look for a long, long time, you'll see the planet pass in front of the star, and it will obscure some of the light that you see in your telescope. And that's how you know that there's a planet. It'd be similar to if this was a star and the tip of my pen is the planet, and as we pass in front, we reduce some of the light that you see in your eyes. Your eyes are the detector here,
Mhm.
and it's probably not to scale, but that's how we do transits. And transits give you some interesting data. They'll give you the size of the planet passing in front of the star. It'll give you the orbital parameters. It can give you some sense of what the atmosphere is, not all the time. It's good for finding bigger planets, and it's good for finding planets that go very rapidly around their stars. So that would be planets that are closer to their stars. The downside on transit is you have to be looking directly at uh, at the edge on of the pass. So you have to be looking at the star this way so that the planet goes around like that. If it's like this, you can't see it pass in front of the star, right? So it has to be edge on, and that edge on view from Earth is about 10% of the stars. But transits are the most prolific discovery method. About 80% of the 5,500 exoplanets have been discovered from transits. The next method is radial velocity. Radial velocity is measuring the planet's gravitational pull on the star as we see it from Earth. And so as the planet orbits the star, the planet pulls on the star, and it changes the speed at which the star moves relative to us. And we can look at that change and detect that a planet is there and a planet is causing it. And again, from doing that, we can detect how circular that planet's orbit is. We can detect how the orbital period, so how often does it go around the star. It gives us a lower limit estimate of mass, so that's very good. Radial velocity, although radial velocity was the earliest method to detect planets, that's how the first ones were detected. Um, Now radial velocity is primarily used to confirm transits. So you put the two together, and if you get a lower limit mass from radial velocity, an estimate of mass, and then you get an estimate of the radius of the planet, you can then derive some other things. You can derive density, for example. You can derive uh, other things from the radial velocity. The limitation of radial velocity, though, is the detectors have to be very, very precise and sensitive. They're very, very picky little things. Radial velocity is best with cool stars, and it works best with larger planets that are close in to their star. Third method, gravitational microlensing,
Mm.
is a uh, phenomenon we can attribute to the great Albert Einstein. And essentially what you're doing in gravitational microlensing is when you're looking at your target star, the star you want to see a planet around, behind that star is another star shining its light towards your detector, towards the Earth. And there's a phenomenon that the stars move in such a way so that the light from the star behind gets bent and gets amplified in your detector. And so what it does, it amplifies whatever is there. And if a planet is there, you get to see it a little better. And microlensing is very good for giving you a little more detail about that planet. It gives you a better estimate of mass. It gives you planets that are further from the star uh, uh, in a better way than transits or radial velocity. Problem with microlensing is it's not predictable. So you have to be
Hmm.
looking at a lot of stars simultaneously, figure out when a microlensing event occurs, where it's occurring, train your camera that way, and hope that you see a planet. So you've got to have a pretty large survey.
So you kind of use the light bending, right?
Light bending, yeah, the bending of light, the phenomenon of bending of light is called an Einstein ring or an
Mm.
Einstein lens. So the light bends around the star that you're looking at and it creates a lens. And that lens then amplifies whatever is in the lens, whatever's in the field of view of that lens. And if it's a planet, you'll see the planet. You'll see it in more detail than you would if that lens didn't exist. But the limit of the lens from a time perspective is kind of unknown, and when it occurs and when it's when it begins, when it stops, when it's going to occur, we don't know. So you have to really concentrate on a pretty wide field of view, and you have to hope that one of them happens.
Hmm.
um, you can the fourth method is direct imaging, which means take a picture. So you take a picture of a star, and essentially, you got your star again, and then you put a shade in front of it to shield the light from the star. And hopefully, by doing that, if I had a third hand, I could put the put the pen back up, but I won't do that. Um, so when you shield the light from the star, what you do is you basically leave remaining the light from a planet. And if you think about it, that helps quite a bit. The light from a star is billions of times more bright than a light from a planet. 1 to 3 billion times, depending on the star and depending on the planet, more bright than a planet. So if you remove that many billions of times intensity of light, you can see planets. And so what that does, because it's a direct image, you get a better sense of what that planet's atmosphere may be composed of. You get a sense of perhaps how the planet spins. You may get a sense of mapping, not surface features, but more atmospheric kinds of features on a planet. Um, the limitations to it are the brightness of the star, right? It's kind of hard to do that, especially from far away. And really, direct imaging, you're going to do from space. You're not going to do it from the ground. So you need a space platform for that. And then the final method is astrometry. And astrometry, basically, what astrometry does, uh, a corollary to radial velocity. You're looking at the star, you're looking at some effect on the star. And so the effect you're looking on the star is the planet. We know the planet pulls the star around. And in addition to changing its velocity relative to Earth's velocity, to how we see it from Earth, you're also changing its position relative to other stars in its local neighborhood. And so you're looking at the change in position. Generally, I think it's 3 stars that you got to look at for every target star, 3 or more. We've only found a few through astrometry, but that method's going to increase, I think, over in the future. High level precision required, and it's generally better for targets close into Earth, but you get a better sense of mass and the orbital period with astrometry. As I mentioned before, transit is the predominant method now. Radial velocity was the predominant method, say, from the 90s through the early 2010s. But transits have taken over with Kepler and TESS, and transits have detected about 4,000 of the 5,500 planets. Radial velocity maybe 1,000, and then the others have done those last couple of hundred. Now there are some inherent issues with how we see stars using these methods, and they take shape in the form of biases.
Mm.
Because our methods are inclined to large planets close in to their star, that's what we see. So we see planets that are the size of Jupiter or much greater, that orbit their stars. A year for those planets is maybe 5 days or 10 days, or sometimes less than that, or less than 100 days. So very, very quickly. Big stars that move, big planets that move around their star very quickly. We tend to see stars that are planets that are much larger than Earth, much larger than Venus, much larger than Mars. We don't see a lot of planets our size. That's just a limit of the detector. We don't see many planets further out than perhaps the distance of Earth to the sun. So that would be an astronomical unit, about 100 million miles. Beyond that, our capabilities are somewhat limited. And so the sample of 5,500 planets is biased by our limitations of our detection methodologies. And so the data that we get is also a little bit biased, because it's not only limited by our detection capability, but it's limited because we haven't seen the vast majority of the population out there. And so we're going to need more data and more help to get a better handle on what is the exoplanet population, what is it composed of, and how does it look relative to us.
So that's when I come in with, okay, so there was technology, right? So I
Mhm.
think technology can improve that. So
Right.
there was an AI algorithm design by researchers at UC Berkeley, and then they mentioned this could solve a lot of problems in terms of discovering exoplanets. And you mentioned bias and also the amount of data.
Mhm.
So how this new algorithm can help and improving the process of discovering this exoplanets.
Okay, so yeah, there are quite a few efforts with AI and exoplanet. I'm not an AI person by any means, but there are quite a few early pioneering methods to use AI to better define the exoplanet population. And if you think about what the issues are, all right, go back to the sample. So we have 5,500 in our sample, and we have for them, oh, maybe 80% of them we understand the size at some level of precision, and for 20% we understand the mass. It's really hard to make conclusions about just that 5,500 sample, much less the bigger sample of everything that's possible within our galaxy, or any classifications that we make within that 5,500. And so AI AI can be applied to do a couple things. One, as we get more data, AI can be used to help us classify what we're finding. And that's a big issue, because how we classify things today are based on our experience here in the solar system. Even some of the names that we use for exoplanet classifications, hot Jupiter means a very large planet that orbits its star at a very close distance and moves very quickly around its star, right? So that's a term, hot Jupiter, that's kind of related to our solar system. But that also is a term that's developed based upon the bias that we have, because our solar system is the only example
Mm.
that we can look at. And when we look at the exoplanet population, We don't see any solar systems that look like ours. We don't see anything that's close to what we have in our what we know is here in our solar system in terms of planets, in terms of how they're spaced, in terms of what they're composed of, in terms of how many there are, in terms of the other things. We don't see planetary moons. We don't see the asteroid belt or anything like Kuiper belt or the Oort cloud around other solar systems. So we're using our own experience to classify this small sample, and that may be correct, but it's probably not. And so AI can help us because AI can remove, if it's done correctly, can remove some of those biases and can perhaps find patterns in the data that we wouldn't be able to find, or our biases wouldn't allow us to see. And I
Hmm.
think that's a huge issue, is planetary classification.
That's
Um,
interesting. So I'm trying to understand. So I didn't. Now I'm trying to understand the importance of this. So scientists look at data, but it might not be accurate because we are comparing basically the only thing that we know, which is our solar system. So if there is any data in there, we wouldn't be able to recognize it anyways. Probably no, most likely no. And then AI can use all that data to come out with a more accurate description.
Maybe the data is accurate within some level of uncertainty, right? We assign some probability that the data is accurate or not, and we can couch how accurate our data is by uncertainty. Um, but what we can't do is can we make we can't make broad conclusions, general conclusions about the exoplanet population that we've discovered beyond kind of some overview things, right? We know there are planets around almost every star we look at has planets. That we see planets that are rocky in nature. We see planets that are gas in nature, hydrogen, helium gas in nature. We see planets that are ice gas in nature. Okay, we see that. Um, we don't see anything that looks like our solar system. We haven't seen, although we have suspects, we haven't seen liquid water on the surface of the planet yet. We haven't fully categorized the atmosphere or how these planets formed, how they migrated to their current positions, at what stage is the system in its evolutionary process. Is it young? Is it old?
Mm.
We don't really know. Um, we don't know the age of the host star. We only know the age of one host star, the one that we orbit. Um, we have some ideas about the lifespans of other stars, but we don't know where they exactly are in that lifespan. And so you know, that's an issue that also is applicable perhaps to some AI applications. And they're just classifying all that so that you can look at a broader a broader population of stars and a much more robust collection of exoplanets as we get data from basically every place we look, and we start looking more and more places. We're going to have to be able to classify that in such a way that is meaningful as we analyze what those planets are, which ones potentially are habitable, which ones potentially could host life today, and then is there life there now as we're observing them? And
Hmm.
time issue is a whole nother issue we can talk about.
Do you know any important exoplanet that has been discovered lately or just recently?
Well, I mean, there are discoveries all the time. I think one of the things that one of the interesting things that came out this week is that what we're seeing and is confirmed is that the planets that are close in, we're looking at um, planets that orbit their stars relatively quickly and are relatively big. That the ones that have uh, that perhaps were within the habitable zone of that particular star may not be so habitable because it's too close and its atmosphere is stripped away. And that's something I think uh, you know might be a little bit sobering. That perhaps our early um, cons- our early conception of how life could form within a planet, on a planet, at it in an exosystem within a habitable zone, um, maybe tempered by the fact that the star it gets that the planet gets too much radiation by being too close to the star, and then the atmosphere goes away, and without an atmosphere, it's going to be tough to generate life and much less sustain it. So that was kind of sobering. I
There,
think.
there, there was something that I read just recently because when I was trying to get trying to get as much information as possible, and I read this about the NASA's Nancy Grace Roman Space Telescope.
Yes.
What is what makes it unique? Because I think it's specifically the goals, for this telescope is just advancing exoplanet discovery using that micro lens
Right.
that you mentioned.
Well, again, not that versed in Roman, but we'll talk about it. I mean, Nancy Roman obviously was very distinguished. Was the first female executive at NASA, and was the driving force behind the Hubble telescope. So uh, she will have this telescope named for her when it launches in the late 2020s, and it will be unlike any uh, exoplanet. It's not an exoplanet specific telescope, but it will have the capability to look across a wider field of view, many stars, for microlensing events, and it will be able to capture microlensing events at a frequency and level of precision that we have not known before. And so you know, that that's actually good with respect to exoplanets, right? It's going to what it's going to do is going to be able to advance that technique. And if you go back, microlensing gives us some stronger data on some of the characteristics of of the exoplanets that are detected through microlensing. That's going to be a big advancement for us. There's one beyond Roman called Habitable Worlds Observer, which is planned for launch in the 2040s. That's a NASA scope as well. And that one is going to be the first exoplanet dedicated mission to look for life signs. So it's going to take known exoplanets in the habitable zone that have confirmed, we'll say, biosignatures, so signs of things that could potentially harbor and sustain life, and look specifically at those planets to see if life in fact exists, if you could actually see if it exists. And that one is, as I mentioned, 2040. So hopefully we'll both be around to see that
What do you think will be the time
one.
um,
For
for
detecting life.
the?
Wow. Um, I hope tomorrow. Um, I hope tomorrow because if we detect life elsewhere, That would be the greatest day in our history. Would be, um, and for a couple reasons. One, because we will have found something we've been looking for a long time and wondering about it and working towards for a long time. But secondly, and more importantly, the discovery of life elsewhere off the Earth hopefully will serve as a mechanism to unify us in a way we haven't been unified, because we will then understand, at least as human beings and as stewards of the planet and as members of all of the, as a representative of all the life species on this planet, that we essentially come out of the same tree, and that we have more in common with each other than we actually realize. And hopefully what that will do will help us put into context some of the crazy divisions that cause uh, problems and violence and pain and suffering throughout our existence here. So I'm hopeful that it will happen. We are looking, in addition to the exoplanet uh, kind of landscape for looking for life, we're looking for life inside our own solar system for evidence of it. We're looking on Mars. We're looking around the moons of the outer planets, around moons of Jupiter and Saturn and Neptune. And there are some interesting possibilities for that. Um, uh, Within Europa, moon of Saturn, has an ocean that's 20 times deep than our deepest ocean under an ice shell. And with the radiated uh, energy that it gets from Jupiter and a little bit of sunlight, there's enough energy within that ocean to perhaps have the ingredients for life. We see around Enceladus, a moon of Saturn, we see geysers of ice spitting from the interior of the planet, which is uh, characterized mostly by an ocean, again covered by an ice shell. And within those geysers, we've actually found phosphorus and other organic elements that could be a formula for hosting life. And so finding another form of life or evidence, existing form of life, or evidence of a pre-existing past form of life, fossilized form of life in our solar system would mean life exists in two places within one solar system. And then if you extrapolate that to the hundreds of billions of stars that are out there in the Milky Way, our galaxy, the possibilities for life there would be exponentially increased. And so that would be a terrific thing. Um, Back to exoplanets, we can't see the corollary of moons of outer planets around We don't have an exo Enceladus or an exo Europa or an exo Titan. We don't even have an exo Mars yet. And so there's possibilities there as well. But it would be very exciting, and hopefully we'll be around to see it.
So, so when scientists discover these planets, they can only see what they're made of. There is no way or technology so far to see if there is any life in these exoplanets, which are really, really far away, anyways.
Not yet. Um, so and there's a couple of issues, right? One is we mentioned our detector limitations, right? So we need bigger, more precise, more accurate telescopes, and we need new instrumentation, maybe some things we haven't thought of, and plus some artificial intelligence to help us manage, massage, and pull out the maximum information we can pull out of the data. So all that's there. But you still have two other issues. You have the distance that you're looking across and the time associated with that distance. So when we look at, say, Earth-like world. I think it's Kepler 22b, I think it is, right? Which is bigger than Earth and a suspect for a water world. I think if you're looking at that one, that's you know many hundreds of light years away. I think it's 500 or 600 light years away. It's a long way,
Oh well, that's
right? So when you're looking at it as it was 500 years ago, right? So the light that you see in your telescope started its journey to you in 1524, right? Before Queen Elizabeth the first, before Henry VIII, 30 years after Columbus. So what would you see, right? Um, if you were looking at Earth, and let's say they were looking at the Earth of 1524, they wouldn't see satellite debris,
Mm.
right? They wouldn't see any evidence of industrial pollution. There wasn't any. They wouldn't see or wouldn't be able to detect radio signals if they're 500 light years away. Radio waves radio waves only began their journey around the year 1900, so they wouldn't have seen that. So you have this time issue for, particularly as it relates to intelligent species, right? You know, when you're looking at it, it's a time machine. You're looking in the past. Um, so that's an issue. And then the second is the distance. So I mentioned Proxima b, the planet that orbits around our nearest stellar neighbor, Proxima Centauri, is 4.2 light years away. And in the press, in our breathless, social media driven clickbait press, it says planet found around our nearest star only 4.2 light years away. Well, 4.2 light years is 25 trillion miles. That's a long way, all right? You're not getting there on one tank of gas, all right? You're going to have to, and you're not going to get there with our current technology. For example, the Voyager ships, which studied the outer solar system and beyond,
Mm.
launched in 1977. The furthest one is 163 astronomical units away from Earth. So it's 163 times further from the sun than Earth is. For that ship to get to the nearest star on its trajectory is going to take 40,000 years at its current speed, and it's going pretty fast, you know, not going
Mm,
slow
yeah, but
by our
I don't think we'll be
by
alive
our
right there.
earthbound speed, right? So for us to get to Proxima Centauri, we're going to have to figure, if we were going to get there, we'd have to figure out some means of propulsion that we don't have, some technology that we don't have any ability to.
So do you
So,
think that this new AI, technology, this machine learning, would it be able to help to detect any type of life that far away?
well, yeah, I think it could. I think if you start at the beginning, right? We have, and again, you're applying our chemistry and our evolution, right, in a very narrow sense to this broad population stuff. So it's not completely applicable, but we know how stars and planets form generally, and if we can understand something about the chemistries of these systems and how they formed and the planets that were formed in the positions that they are as we detect them, um, we can begin to understand compositions of those planets. We can understand where habitable zones are for each of the stars that we're looking at. They differ by stellar type, um, and essentially the amount of radiation that the star produces. Um, we can begin to create models that maybe take a few data points, uh, more data than we have now, but just a few data points, and point us towards places where it's likely that a planet around a habitable zone has the necessary components to harvest life, and then focus a mission um, like a Habitable Worlds Observer, or GEOPS also looks at known exoplanets, or a bigger telescope like the Roman. Can we focus on that particular world and look for things that may be indicative of life, um, and understand that some of the the things that are indicative of life, um, liquid water, oxygen, nitrogen, carbon, sulfur, phosphorus, etc., chinops stuff, uh, amino acids, radiation source, that you can see those things and they can all be there, but life may not result from that. Oxygen, for example, right? We take that as, we need oxygen to live, right? So oxygen has to be a good biosignature, but oxygen can be produced and by methods that are not, oxygen is produced by plants on Earth, life, but oxygen can be produced without life. And so just looking for oxygen doesn't necessarily mean that there's life. You've got to look for this concert of things that are in existence, and AI can help us figure out what all the notes are in that concert or symphony, right? That's
Mhm.
really where I see uh, AI really helping us.
So, what are the main factors? So if you're a scientist, you're trying to discover new exoplanet or life in a specific planet,
Mhm.
what are the factors that you take into consideration? Because you said oxygen is not um, the only thing that we should pay attention, but there are so many factors as well. So, there
Okay.
should be like a list of variants.
There's I mean, uh, so the physical variance, you got to have a star, you got to have a planet, you got to have a planet in a habitable zone. You got to have a planet in a habitable zone that has some components, right? It has liquid water. Liquid water is a solvent. Um, it's a really good solvent because it mixes with a lot of things really well and has a lot of different forms. You got to have the chemistry I mentioned, the carbon, the hydrogen, the nitrogen, the phosphorus, etc., um, oxygen. You have to have some energy. You have to have solar energy. You got to have some chemical energy to get things started. You have to have a stable environment in terms of temperature, salinity, pH, pressure. And then the ingredient that we most overlook is time.
Hmm.
And time is not measured in hundreds of years or thousands of years. It's measured in deep geologic time, billions of years. Life didn't form on Earth until uh, 600 or so million years after the Earth formed, and then it was single-celled life for almost 2 billion years after that, right? And then intelligent life didn't form until 4 million years ago, which is a tiny sliver of the 4.5 billion year lifespan of the Earth, just a really, really tiny fraction. So you need time for life to evolve and reproduce and sustain and grow and branch out. And then you need a lot of time for intelligent life to form and survive and prosper and dominate. And so those are the things that you got to look for. And then you need to make sure that when you're looking for it, and this is kind of a brilliant uh, concept from a good friend, Mark Nouveau, uh, called the ladder of life. You've got to make sure that when you're looking for this, that the means through which you look, your detectors, your instrumentation, are sensitive enough to find it, that they're not contaminated, that you can find it more than once. Finding it once is not enough. You've got to be able to repeat it and repeat it and repeat it over and over. Um, you got to know that you got to be able to determine that the life that you're looking for is somewhat detectable, that it's survivable, that it's not just a momentary thing, that you have a reliable detection, that what you detect, um, because we're looking for life as we know it, at
Mm.
least at this point, is it compatible with the things that we know, or is it something else, or is it from an abiotic process, something that's not produced by life, say like gases out of a volcano, right, are not produced by life, but you could see those on other worlds, and maybe get confused. So is it compatible with life? And then look at all that and say, okay, what else could it be? Right? What else? What have I missed? Because the last thing you want to do is announce that you found life and be wrong. Right? That would, especially in this
Well,
day
that
and
would be
age.
very embarrassing if you do.
Well, not just embarrassing, but you can imagine what the internet does and runs with it,
Mm.
and turns it into controversy and becomes politicized, and all of that, and then your whole effort becomes compromised. You don't want that. So you've got to do, what Mark is advocating is a very rigorous set of steps and processes that are tied to what you do it with, how you do it, how reliable it is, how can you validate it, right? That's what that's the name of the game, is with respect to scientists looking for life.
But then even discovering, let's say, okay, they discover some type of life or um so even if that happens, I'm thinking about, because you mentioned last time the time frame. If
Mhm.
we are very, very far away,
Right.
then whatever you're discovering at the moment might not be there anymore.
Perhaps. Okay. Now we're uh, imagine. All right, and I don't want to take this to a UFO discussion. That's another hour. Okay. But imagine an alien ship that pulled up to Earth 150 million years ago and looked down. What would it see? It would see a bunch of large reptiles with teeth running
Mm.
around. And they might look down and say, I'm not messing with that. There's nothing here, and I'm not coming back. Okay? Just saying.
Mm.
Um, so it's when you detect it. What did you detect when you detect? When they saw those large reptiles with teeth, unless they had really good AI, or better than we had, how could they predict that we human beings would result?
Uh,
I don't know that they could or could not, right? I
so
don't know that
maybe
they
maybe
maybe.
they came to planet Air, just we're
Well,
not here.
okay, but maybe now, 200 million years later, they're extinct. That
Uh,
civilization's extinct, so they can't look. Okay. Um, the same issue with, if if you did one close in, Proxima Centauri, and we found life, intelligent life on Proxima Centauri, 25 trillion miles away. That's the closest it could be to us outside our solar system. And we send them a message. Hi, Proxima Centauri, here we are. They're not going to get it for 4.2 years. And so they'll get it in 2028, May of 2028, June of 2028. So they'll send it back. Hi, Earth, how you doing? And we'll get that in September of 2032. What good is that? What do we do with it? Right? 8-year round trip for hello, how are you? Right? How do we
mm.
deal with that? Um, that's a question, right? For further out, if you're looking at, one of the planet 500 million light years away, what do we do with that, right? If they send us a message in 1524, we're just getting it, and we send it back to them. The people that sent it are long gone, right? Perhaps, right? Unless they have really extended lifespans.
Do you think we will have a type of technology that can solve that problem? I mean, I know that's another topic that has
That's
to do
another
with,
hour, right?
yeah, I know.
Star Trek.
But yeah, but I'm trying to think all this, AI thing and machine learning. If they're creating this type of algorithm that helps, with data and understand and have a more ethical way, I would say, unbiased of discovering new planets, that I think there should be a way, technology can help somehow
Um,
to.
yeah, right. It will help us. It's already helping us, right? It's already doing some of the things we discussed are already being talked about, right? Planetary classification, um, trying to use AI to develop the categories that we need that are not based on bias, um, or that may be a way that we're familiar with, right? The way we look at, say, animal and insect species, right? And we look at, we got all different kinds of dogs, and they trace back through a wolf and back through their ancient ancestors, and we classify them in a biological way. Can we use that framework as a means to classify exosystems and their eventual planets and moons and uh, uh, life possibilities? Can we do it that way? AI certainly can help with that. Certainly would help with that. Certainly can look, um, help us figure out how to get past some of the bias of instrumentation. I think certainly can help that, and I think people are working on that.
All
Um,
right. So,
Lots of possibilities.
as an expert in astronomy, how do you foresee the future collaboration between technology and astronomy evolving?
Um, wow. Well, it's going to continue to evolve. It's going to continue to get better. Um, we've always looked for better ways to look at things from the time, Galileo first looked through his telescope until now. We have all kinds of sophisticated instruments hanging off the telescope. I think, the biggest, from my perspective and my focus, is on telescope observations. Um, Adding CCD cameras, digitized cameras to telescopes is one of the greatest things that we've ever done, because it allowed us to as opposed to, uh, initially when we looked through telescopes, we were drawing pictures of what we saw. I remember doing that in my bachelor days, to actually, then getting a photograph. You get a photograph and then you analyze. Now you get pixels, which are digitized, and you could turn the digitization of the pixels into information, right? That's a huge
That's
advance.
crazy.
And so AI then takes it the next step and says, okay, what are the possibilities beyond what you actually see here? Right? That's one possibility. The other one, which is something that's being done with AI now, and it was done kind of manually and through early computers and more advanced computers later on, is going back through old data of old missions, past missions, and looking at old data and trying to figure out what did we miss. And so the Kepler mission, which ended a few years ago, produced and continues to produce reams and reams and reams and reams of data, systems that it looked at. So there's a group that's got an AI algorithm to apply to the past Kepler data at transit attempts that didn't yield planets, going back and looking through those based on what we know currently and based on the algorithm that we build in AI, did we miss anything in that data? Are there planets
Mhm.
that we missed around stars where we didn't detect planets? Or are there additional planets around stars where we did detect planets, but we didn't see those other ones, right? Those are some good applications for AI. And so the future, and the future is, I think, limitless, right? Where you get to the point where you could have um, space missions where they have the technology through AI on board the spacecraft to repair itself. If you are old enough to remember Hubble, Hubble in its first, one of the first things that happened to Hubble was it had to be repaired before it could be used. But there were several other missions to do tune-ups and upgrade Hubble and to add fuel to it, keep it running. It's still running. Um, and that was using space shuttle. Webb doesn't have that capability. We don't have a technology yet to reach Webb and recover it, and probably not Roman. But could you, and maybe Roman, maybe who knows, and hopefully habitable worlds observer in the 2040s. But could you develop a ship that has the intelligence to repair itself and upgrade itself? Um, that would be interesting to see. Uh, that would be interesting to see. Now, that then brings into, if it upgrades itself, could it then turn around and do some harm? Yeah, I mean AI itself, not necessarily a ship. We don't want AI eating us on Earth, right? But repair itself, right, would be good enough. Not make war,
I think that might be
clone itself,
possible soon.
not clone itself and make war. No, we don't want AI doing that from space,
Not,
but
not
to
taking over
repair
the
itself,
world.
right? And to advance itself, right? That would be something that would be remarkable and useful.
Thank you so much, Gordon. I think we have hit the time, but I really thank you so much for giving all this information. It was so instructional. Um, and we'll definitely have to do this again, but a different topic.
Thank you, Zara. I look forward to it.
Thank you. Bye. Thank you so much for watching. This is Zara, your host, Little Wild Experiences, and please comment below, subscribe, and give us more ideas for topics so we can give you more content. Thank you. Bye bye.